At 1:23 in the morning on April 26, 1986, an operator at the Chernobyl Nuclear Power Plant pressed the emergency shutdown button. The button was labeled AZ5. It was supposed to kill the reactor in seconds. For the first 3 seconds, it made the reactor more powerful instead. But to understand why a shutdown command could cause a power surge, you need to understand what kind of reactor this was. The RBMK 1000 is a Soviet design. The acronym stands for High Power Channel Type Reactor in Russian. The first unit went critical at the Leningrad Nuclear Power Plant in 1973. It is graphite-moderated and water-cooled. Those two facts are the center of the story. In a Western pressurized water reactor, water does double duty. It cools the fuel and it moderates the neutrons, slowing them down so they can sustain a chain reaction. If the water boils away, moderation drops, the chain reaction slows, and the reactor loses power. The physics are self-correcting. Lose the coolant, lose the reaction. The RBMK splits those jobs. Graphite blocks do the moderation. Water only cools. This means that if the cooling water boils, graphite keeps moderating neutrons just fine. But the steam bubbles that replace the water absorb fewer neutrons than liquid water did. More neutrons reach the fuel. The chain reaction accelerates. Engineers call this a positive void coefficient. When voids form in the coolant, reactivity goes up. The reactor gets hotter when it should be getting cooler. Soviet nuclear authorities were aware of this property. Information about the positive void coefficient was restricted and did not appear in plant-level operating documentation. In a Western PWR, boiling water is a brake. In the RBMK, boiling water is an accelerator. That difference is the first half of the Chernobyl story. The second half is the control rods. The RBMK has 211 control rods. Their job is to absorb neutrons and regulate power. The absorber section is boron carbide, and it works the way you would expect. Push a boron rod into the core, neutrons get absorbed, power drops. But the bottom section of each rod is not boron. It is graphite, about 1.25 meters long. This graphite section is called the displacer. When the rods are fully withdrawn, water fills the channels below them. When the rods begin to descend, the graphite displacer enters the channel first, pushing out the water. Graphite is a better moderator than water. Replacing water with graphite at the bottom of the core, even briefly, increases the local neutron flux. If the core is already in an unstable state with steam voids forming, inserting the rods causes a short reactivity spike before the boron section arrives to absorb it. This is the positive scram effect. The emergency shutdown, for its first few seconds, adds energy to the system it is supposed to shut down. The effect was identified within the Soviet nuclear establishment and independently confirmed by the U.S. Nuclear Regulatory Commission's 1987 technical assessment. Yet the rod design was not changed, and the risk was not documented in operator procedures or training materials. The test was straightforward in concept. Simulate a station blackout, cut steam to the turbine and measure whether the spinning turbine could generate enough residual electricity to power the coolant pumps for the 40 to 60 seconds before the backup diesel generators started. This test had been attempted before and had failed. It was rescheduled for April 25, 1986, during a planned shutdown of Reactor 4. The plan called for running the test at 700 megawatts thermal, a low but stable power level. The first problem was a grid demand delay. The power reduction was paused for hours while Chernobyl continued supplying the grid. When operators resumed the reduction after midnight, the power dropped too far to about 30 megawatts thermal. At this level, xenon-135, a fission byproduct and strong neutron absorber, had built up in the fuel. Xenon poisoning was smothering the chain reaction. To restore power, operators withdrew control rods far beyond the procedure limit. The operating rules set a minimum operational reactivity margin, called ORM, equivalent to at least 15 fully inserted rods. By the time the operators finished withdrawing rods, the ORM had fallen to the equivalent of 6 to 8 rods, far below the safe limit. They brought the reactor back up to about 200 megawatts thermal, well below the planned test level. The reactor was now in a state its designers had warned against: low power, high xenon, minimal control rod insertion, unstable coolant flow. The operators had violated multiple safety rules to get there. Procedure required aborting the test at this point. The test team decided to proceed. The design flaws in the RBMK were real, but the operators created the exact conditions that made those flaws lethal. At 1:23:04 a.m., the test began. Steam to the turbine was cut. The turbine began to spin down. The coolant pumps, now running on the decaying turbine output, slowed. Coolant flow through the core dropped. Water began to boil. The positive void coefficient took over. Steam voids formed. Reactivity rose. Power began to climb. Within seconds, the operators recognized the surge. Someone pressed AZ5. All 211 control rods began to descend into the core. The graphite tips entered first. At the bottom of a core already filling with steam voids, they replaced water with graphite, adding moderation where the reactor least needed it. The positive scram effect was catastrophic. Multiple post-accident analyses, conducted independently by Soviet, IAEA, and US NRC teams, estimated the power spike reached at least 30,000 megawatts thermal in under 3 seconds. Some models placed the peak considerably higher. The design output was 3,200. Fuel pellets shattered, pressure tubes ruptured. A steam explosion blew the 1,000-ton upper biological shield off the reactor vessel and through the roof of the building. A second explosion followed within seconds. Burning graphite and reactor fuel were scattered across the plant grounds. The emergency shutdown had destroyed the reactor. 2 plant workers died in the explosions. 28 emergency responders, mostly firefighters and first response operators, died of acute radiation syndrome in the following weeks. Those figures are consistent across Soviet, IAEA, and UNSEER records. The Soviet government ordered the evacuation of Pripyat, the workers' city 3 kilometers away. Roughly 49,000 residents were bussed out beginning 36 hours after the explosion. Soviet civil defense records and later IAEA and UNSEER reviews report consistent figures for both the population and the delay. A 30-kilometer exclusion zone was established. Over the following years, the 3 affected governments resettled more than 350,000 people from contaminated areas across Ukraine, Belarus, and Russia, a figure reported independently by both the IAEA and WHO Chernobyl Forum and UNSEER. Between 1986 and 1990, roughly 600,000 workers rotated through the contamination zone, according to figures cited independently by UNSEER and the Chernobyl Forum. They were called liquidators. They shoveled radioactive debris off the reactor roof, built the first concrete sarcophagus around the wreckage, and decontaminated roads and buildings by hand. Many received significant radiation doses. The long-term cancer toll remains genuinely uncertain. The WHO and IAEA jointly estimated roughly 4,000 eventual excess cancer deaths among the most exposed populations. UNSEER's assessment supports a figure in the same order of magnitude, but emphasizes the difficulty of isolating radiation-induced cancers from background rates. Other analyses, using different dose-response models, place the total significantly higher. The range of estimates reflects real scientific disagreement about low-dose radiation effects across large populations, not just political framing. The Soviet response was immediate and technical. Every RBMK in the fleet was retrofitted. Control rods were redesigned to eliminate the initial reactivity increase on insertion. Additional fixed absorber rods were installed in the core to reduce the void coefficient. Fuel enrichment was increased from 2% to 2.4% uranium-235, which further reduced the positive void coefficient at low power. These changes are documented in both INSAG-7 and subsequent IAEA safety review missions to the remaining RBMK plants. Emergency insertion speed was improved. Rods that took 18 seconds to fully insert now take 12 seconds, with no reactivity adding phase at the start. Operating procedures were rewritten to prohibit running below 700 megawatts thermal with reduced control rod insertion. The institutional changes were larger. The Soviet Union, a country that had treated nuclear accidents as state secrets, agreed to the IAEA Convention on early notification of a nuclear accident in 1986. 8 years later, the successor states and the broader international community adopted the Convention on Nuclear Safety in 1994. The World Association of Nuclear Operators was founded in 1989 to share safety data across national boundaries. The disaster at Chernobyl was not the product of a single cause. The RBMK's positive void coefficient and the positive scram effect were genuine design defects known to Soviet authorities and not documented in plant procedures or training materials. The operators, in turn, violated safety limits that existed precisely to keep the reactor out of unstable states. Both the machine and the decisions around it failed. The institutional lesson was that design-basis safety information cannot be restricted from the people running the reactor, and that safety systems must function under the abnormal conditions that are the only reason anyone presses the button.